It is Martin Luther King Jr. Day, and I was looking at the course calendar and the sections and realized it would be really horrible if we tried to fit this section and the next section all in 55 minutes on Wednesday. So I'm going to record 1.4 separately so that you have a chance to actually get everything out of the section without me rushing through it. And then that way, when we actually meet in person for 1.5, should be good. I'll have time for questions. There should be better pacing. So make sure you watch this recording before, obviously, going to 1.5, because otherwise it won't really make that much sense on Wednesday. This is the matrix equation. Now, we've already kind of talked about some of the stuff in here, so not everything in here is going to be really new. Just again, more perspectives of the same stuff. So the matrix equation, and it's going to look like AX, a vector, equals B. Okay, let's start with the definition, as we usually do with these sections. If capital A, let me know recording, okay, yeah, is an M by N matrix with columns, and this will explain why we had that notation on last Friday's lecture, I think. Columns A1 through AN, and if I have some vector x in Rn as well, notice these subscripts are important. The subscripts are important. I have n column vectors because that's what it means for a matrix A to be an M by N, rows by columns. Okay, so if n is the number of columns, that's how many columns I should expect to have as column vectors, and that's exactly how many entries I would want my x vector to be. Then the product, I'm going to do another type of product here, the product of A and X, of A and X, denoted, and I've already written it at the top of the section, AX, is the linear combination, of the columns of my column vectors, so of the columns, you can think of that as my list of A1 through AN, columns of A, using the corresponding entries in X as weights. That is, so that's all the English. So we can actually just describe all of that English with some math notation. That is, I could say that AX, which, if I describe A with the column vectors, I know that A has n columns. So I have column vector 1 through column vector n. Notice that this is not an augmented matrix because I only want the column. So this would, we would think of this as more of a coefficient matrix. So know the difference. There's no augment. And then we're multiplying this by the vector x1 down to xn, because that's how many entries it has. How do I know that? Well, because it says it right there. This is going to be, this is a very, very familiar equation if you've been paying attention. x1, a1, plus so on and so forth, xn an. Vector equation. Matrix equation spits out something that's basically close to a vector equation. This is the linear combination. You're associating your columns with each entry of the vector. Okay. So this is important. Have this. We'll do a quick. Actually, this does imply a rule that I should just state down here. So I'll star it. It's not really a rule so much as it is this is undefined if what I write isn't true. We only have AX being defined only if A is m by n, so it has m rows, n columns, and X is in R n. Why is that important? Well, it's just logic. If your matrix has n columns, then if I'm going to match up the same exact number of weights, coefficients per column, I kind of need exactly the same number of entries here in X as I do columns. So X has to be Rn. That's not really, otherwise what are you doing? It's impossible to even take that product. The product is an undefined notion if I don't have enough entries here to match the number of columns. Okay. Let's do an example and just do some basic computation. So if I have the matrix 1, 0, and when I'm speaking out loud, I will speak out the column vectors. So 1, 0, 2 minus 5, minus 1, 3. And that's that. And I'll multiply that by the vector 4, 3, 7. Okay, so by definition, what I'm supposed to do is I'm supposed to take each column and then take that column and multiply it by a corresponding entry in the vector. So the first column here is 1, 0, and the first entry is 4. So I take 4 and I multiply it by the first column, which is 1, 0. And this pattern is going to continue. What's the second entry of my vector? 3. And then what's the second column of the matrix? 2 minus 5. The pattern continues. What is the next vector entry? 7. And what is the third column? Minus 1, 3. Okay. Now, this is written in a way that we know how to handle this. This is just, we can scale these vectors up. 4 times 1 is 4, and 4 times 0 is 0. Plus 3 times 2 is 6. 3 times minus 5 is minus 15. Whoopsie. 7 times minus 1 is minus 7, and 7 times 3 is 21. Now, when I'm adding these vectors together, I'm just adding all of these components up. So 4 plus 6 is 10, minus 7, 3. 0 minus 15 plus 21, 6. Okay, so there we go. Let's do another one. Here's the first vector. Again, when I say it out loud, these numbers, I'm saying them as column vectors, not across. 2, 8 minus 5, 2, 8 minus 5, minus 302, minus 302. And I'm multiplying that by the vector 4, 7. Okay, so let's go through this process again. What is the first entry of the vector? The first entry is 4. And then what's the first column of the matrix? 2, 8, minus 5. 2, 8, minus 5. Okay, what's the next one? 7. And what's the second column? Minus 3, 0, 2. So I scale. 4 times 2 is 8. 4 times 8 is 32. 4 times minus 5 is minus 20. Scale the next one. 7 times minus 3 is minus 21. 7 times 0 is 0. 7 times 2 is 14. I think you get the gist of it now, yeah? So we have negative 13, 32 plus 0 is 32, and minus 20 plus 14 is minus 6. So that's doing these computations really isn't that difficult. Okay, the computation itself is pretty straightforward. Here's another example. We can think of translating the relationship between all of the perspectives is important. So if I have vectors v1, v2, and v3 in R, let's say that they have how many entries? It doesn't really actually matter, but here, let me go back. Let's have, sorry, okay. If I have a linear combination of some vectors, so like maybe 3v1 minus 5v2 plus 7v3, if you're given a linear combination of vectors, we can actually express any linear combination of vectors as a matrix, like a matrix times a vector. So what would the matrix be in this case? Well, let's just reverse engineer the concept. Look at all these. All of these column vectors are the vectors, and then those weights are those constants out front. And so, like if this 2, 8, minus 5 is the vector that corresponds to the first column of the matrix, then the first column of the matrix is going to be like this v1. And if this minus 302 is that second column of the matrix, then this second vector, v2, is the second column of the matrix. And then same kind of reasoning for that third column. So here's my matrix. The matrix listed as these column vectors. And what am I multiplying them by? I'm multiplying them by these scalar weights. In order, it would be 3 minus 5, 7. So 3 minus 5, 7. And to double check that work, if I started with this side of the equation and then computed and simplified it, I would just spit this out. Okay? So get used to moving between those two perspectives as well. Okay. Now let's learn how to go from a system of equations to a matrix equation. So a system of linear equations translate that to a matrix equation. So say I had x1 plus 2x2 minus x3 is equal to 4. Then minus 5x2 plus 3x3 is equal to 1. So this is a linear system of equations, right? So this is a linear system. Linear system of equations. And we want to make this look like a matrix equation. And so recall from the lecture on Friday that one way we can easily view a system of equations as a linear combination of vectors, column vectors, is you should have practiced doing this. We can get this to a vector equation. So in other words, I'm thinking about these splits, right? And so my x1 has coefficients 1 and 0. My x2 has coefficients 2 and minus 5. My x3 has coefficients minus 1 and 3. And that is equal to, obviously, then the 4 and the minus, or the 4 and the 1 on the other side of equals. So this right here is what we call a vector equation. This is what we talked about Friday in 1.3. Okay, so now from a vector equation, we just showed previously that if I have a vector equation, I can write this as a matrix equation. So we're just going to do that again. So I can write this instead as a matrix. So the matrix A is comprised of putting together these column vectors. Here's the first column vector, 1, 0. Here's the second column vector, 2, minus 5. Here's my third column vector, minus 1, 3. And then the vector x has what components? x1, x2, and x3. And we know that this needs to spit out 4, 1. That is a matrix equation. Okay. Where we can understand... Oh, someone's watch is going off. This is our matrix A. That this is the vector x, and this is vector b. Okay, now you'll want to be able to go really between any of these in one step. So if I wanted to go between this linear system and this matrix equation, I should be able to just recognize, take the coefficient matrix, then list the variables in a vector, and set that equal to, turn into a column vector, whatever is on the other side of the equation. So this is not difficult. You just gotta practice it a few times, do it yourself, because if you only watch me do it, then you probably won't make that much sense. Okay. There's an important theorem, and I'm going to write it first in words, and then after I write it in words, I'm actually going to describe that theorem exactly the same way, but just with a more visually intuitive kind of graphic. So if you like doing these things with the words, here you go. If A is an M by N matrix with columns A1 to AN. Again, n columns for n by n, and if B, so on the other side, is Rm. Okay, so we switched from M. Why is it M now? It's because when we were doing these previous problems, whoopsie. Let me go to the example. When we were doing these, check this out. Rows by columns. 3 by 2 meant that we needed a 2 by 1. And then that spits out a 3 by 1. And 3 is the number of rows. Rows by columns. We need the number of entries in this vector to be the same as the number of columns. And after you do that computation, it will end up giving you, basically you spit back the rows, the original row amount, so the m value. So here, rows m by columns n. So I have my n columns, and now on the other side, that b needs to be, as we saw, actually it'll have the same amount of rows, m. The matrix equation, ax is equal to b, has the same solution set, as the vector equation, x1, a1, plus so on and so forth, xn, an is equal to b, which we've seen that quite a few times already, which in turn has the same solution set, as the system of linear equations whose augmented matrix is, and then we've seen this a bunch of times too, right? A1 through AN, and then since this is augmented for a system, then we do have the B there. Okay, that's a lot of words. I personally don't like the word version, so we'll do the math version in a second. And basically, yeah, what we've been talking about, this matrix equation, all this is saying is that on top of all of the perspectives for solution sets that we had on Friday, all of those perspectives now have a new buddy, which is going to be the same thing, just a new perspective with the ax equals b. It's another way to write it. It's a new cosmetic way to think about it. Yeah. So don't think of it as a completely new concept. It's really just the same as what we've been doing in terms of its solution set. It just looks a little bit different and is a useful perspective that we will take advantage of later. So here's what I think is the more helpful way to think about this. So in the center, they're all going to circle the same solution set. So I'll put that in the middle here. So the same solution set. So this is what they're all circling in the middle here. We're obviously talking about the matrix equation in this section. Ax is equal to b. So this is our matrix equation. And then from the matrix equation, what really does it mean to have the A as an m by n? So we could think of that as having re-express the matrix in terms of its columns as column vectors. So A1 through AN. And then that means, since I have n columns, I must have the same number of entries for my x vector so I could actually multiply it out. And then my b vector, the output, needs the same number of rows as these column vectors. So Bm instead of n. Okay? So this is kind of just this is a expanded view of the matrix equation. So they're the matrix equations. Those have the same solution set. Do they look a little different? Yeah, but what this is really just doing is this is A, this is X, and this is B. So nothing really new other than just mathematically how we notate that, okay? But what we can do that changes perspective is actually multiply this out to make it a vector equation. So I could have x1 times the first column a1, so on and so forth, until I get through to xn, the last entry times the last column, all of that equaling the vector b. So I could have this perspective, which is what we learned on Friday, the vector equation perspective. So this is the first time where cosmetically this does look different than the matrix equation. But they're all the same. They're all describing the same solution set. And further than that, we knew earlier from last week that this vector equation is really just describing the solution set that's the same as having an augmented matrix of a linear system where these column vectors were the coefficients. So a1 through an, and then making it augmented with that b vector. This augmented matrix. Augmented matrix. And those are equivalent. And you can get there from there as well. I like to think of this right here as the implied A, and obviously that is your B, and then the X is implied because it's the augmented matrix of a linear system, which is going to have variables x1 through xn, which we can describe as the vector x. Okay? All of these perspectives have the same solution set. Same solution set. So this is very similar to Friday's, where we had a bunch of different perspectives, same solution set, nothing has really changed. We've added to our augmented matrix the vector equation, and from there we've now added the matrix equation. And these are going to be kind of the main fighters for linear algebra. Okay, this is really important. Be able to switch between these, because certain facts about matrix equations, for example, seem like they're kind of interesting, but in reality they're restatements of things we already know based off of the other perspectives, since they all have the same solution set. One of those facts is a theorem, whoopsie, which is that the equation, so we have a matrix equation here, AX is equal to B, has a solution So basically, if I claim that this matrix equation has a solution, I could have logically and equivalently stated that the vector B is a linear combination of the columns of A. And you might be thinking, okay, well great, more to memorize. No, not really. Think about this. They have the same solution set. So if AX equals B has a solution, that is, I can find correct weights in X so that whatever this all the columns in A end up spitting out B, then yeah, that's basically the same thing as saying that B is just a linear combination of these columns of A. In other words, if there is an X here, a solution that makes AX equals B, then knowing that that is the exact same perspective as this vector equation, reframing this is saying that, okay, yeah, so there's a solution. That means I could find x1 through xn, specific weights. I could find a linear combination that spits out B. This having a solution means that such a value has to exist. So then, by nature of just viewing it through the vector equation perspective, then it's obvious. Of course, then. B, if it's still a solution, then there has to be a linear combination of those columns. So that's all this theorem is saying. It's not a hard theorem, so long as we have this in mind. If we don't have this in mind, then this can just seem like something else to memorize. That's not really how you want to learn math, because there's a lot of random facts that are going to happen, and you're not going to keep track of all of them. So anchor yourself to this kind of stuff, conceptual stuff, the fundamentals, because the consequences they'll make more sense. Okay, let's go through another theorem. And this one I'll use to actually teach you some math notation for the class. Theorem. So let A be an m by n matrix. M by n matrix. Then the following statements are logically equivalent. Logically equivalent. Again, so that basically what to be logically equivalent is, if I say this, then all of the other ones are automatically true by default of this one being true. And if this is false, all the other ones, just by logical default, are also false. Okay, first thing here. For each B in Rm, very important, the row number, the equation basically the matrix equation Ax equals B has a solution. Let's see what this is really saying. So the first statement here is the claim that no matter what I choose for B, this equation's I could always find an x that multiplied against A could get me to B. So no matter what I choose for B, no matter what this outcome is, I can always find an x, at least one x, so that that will actually be a true equation. That's really what's being said here. How can I say this more efficiently with math? For each, I use the upside down capital A, so for each B in Rm, what am I claiming? Well, in English, as I was describing it, that I can always find a solution x, no matter what. So basically, there exists, that's what that one, there exists some x. How many entries do I know x has to have? It has to have n. It's the same as columns. Such that, this is a new one, this symbol means such that. Okay, so this is such that. There's a lot of different such that symbols. This is one. Such that Ax equals B. Okay, so I'm basically saying, no matter what I choose for B, there exists some solution such that the equation is still good. Okay, that's the first statement. Let's see what else. Let's see what other statements logically follow from this. If that's the case, then each B in Rm is a linear combination of the columns of A. We just talked about this, of the columns of A. We already talked about this. Basically, this is saying that, okay, if it's true that no matter what I choose for b, so I could put whatever I want in there, I'm guaranteed to have a solution. Okay? If that's the case, it's then logically equivalent to be like, all right, so then no matter what I choose for b, because I'm guaranteed to have a solution, that means I'm guaranteed to have precisely the weights I need to describe that b as a linear combination. So I could say there exists my solution x in Rn such that I could just write b as that linear combination. x1a1 plus through xn an. Again, think about the vector equation perspective as does here. This matrix equation having a solution is going to be the same exact thing as this having a solution. So if I claim that no matter what I choose for b, that this is going to have a solution, then that's basically just saying switch the perspective over to the vector equation. And there has to be these weights x1, xn, so that I have essentially a solution. So this x is still going to exist, and instead of writing it as the ax equals b perspective, I can write that as the, whoopsie. How do I move it back? Oh my goodness, okay, there we go. Okay, and then I can do it with the vector equation perspective. Okay, another statement. If that's the case, then that means the columns of my matrix A span Rm. Okay, so how do I want to say that in math? Basically, I could just say that the span, what are those columns? Well, we've been calling them A1 through AN. That should spit out Rn. Okay, recall what span was in the previous lecture. Span is going to be all the possible linear combinations. So let's think about the ramifications of this. If ax equals b always is guaranteed to have a solution no matter what I choose for b, then that means, and so again, think about that. That means no matter what I choose for b, there's going to exist a linear combination for me. So no matter what b I choose, essentially every b in Rm guaranteed to have a solution. Okay, well, sure sounds like the whole set of all of the possible linear combinations is what we meant by the definition of the span of those vectors. So this becomes true definitionally. That the span, all possible linear combinations here, is going to be all the possible linear combinations here. And since I'm guaranteed to have, no matter what this b is, that's essentially all of the possible vectors in Rm. So that span is going to be Rm. And that, again, by nature of being related to the middle statement, is related to this first one with the matrix equation. And then the last one is that A, the matrix A, has a pivot position in every row. So, I mean, there's not many math symbols here we can say here, but for all rows, basically, for each row of A, there exists a pivot, so I can say it like that. And what does that really mean? When I had recall back in this perspective, if I decide to notice that with the augmented matrix, the A is only the coefficients, okay? And so if I want A to have a pivot in every single row, then what I'm basically guaranteeing is that I never end up with an awkward situation where I'll have a row of all zeros, for example. Because if I have a row of all zeros, then that's a problem there. I'm not going to have a solution. So if I know for certain that no matter what I choose, I have a solution, then yes, this makes logical sense. Certainly, all those coefficients there's going to be a pivot for every row to guarantee that there can be that solution every single time. Okay. So understanding this theorem is really so much just, did you really understand the ramifications of this? Understand the ramifications of this will give you that, and it will give you that. So take time to think about it. Don't rush past this. Mull over it. Know for yourself that you can make the mental pathway between each of those. All right, so just a few little things here, and then we're done. We already did some computation, but I'm going to show you, when we did the computation, it was kind of like, it took a while. It was a little bit tedious. And so there is a faster way to think about this, and I'll show that to you. So let's do this. Again, when I say it out loud, these are the column vectors I'm saying. 1, 0. Actually, let's do the same problem as we did before. So 1, 0, 2 minus 5, minus 1, 3, minus 1, 3, times 4, 3, 7. So we did this as the very first thing in the lecture. But we kind of, what we did was, from the definition, we went the entry times the column, entry times the column, entry times the column, and then we had to scale each of them individually, and then we put them together. We really could do this in one step, okay? And so the algorithm is going to be like this. I shouldn't have written it so high up. I'm short. Okay, I'm going to move it down. There we go, okay. So the way this works is, we're going to form a dot product where we start here, and as we go across, we start here and go down with the entries. So notice that the same number of columns is the same number of entries. You've probably heard me say that now 4 times in this lecture, okay? So same number of entries, and so that's how we're going to form the dot product. It's going to be 1 times 4. So I can immediately just go here and say 1 times 4 plus 2 times 3, 2 times 3, plus minus 1 times 7, plus minus 1 times 7. So I don't need to go through, I mean, it's good to go through the whole thing of knowing that you can take the entry times the column vector and then scale. But if you are just trying to do a basic computation, this is how you can do it. So then we continue with the next row. So again, you start on the left and you move over to the right. And then again, you're going top to bottom. So the way I like to visualize is I kind of go on my paper, and with my fingers, I'll start like this, and I'll do that to remind myself of the order. And then I'll go to the next one, and I'll remind myself of the order. So then 0, if we're doing this, right, 0 times 4, oops. And we're continuing. Minus 5 times 3. And then continue on. 3 times 7. So then, obviously, you can do the arithmetic. It'll just be 3, 6. But if you wanted to go in one step from here to, wow, I don't understand. If you want to go in one step from here to here, then you can do so with this kind of algorithm. All right, and then if we know that type of algorithm, it's actually kind of an interesting thing that happens, and it'll motivate a definition that's really easy. Say I have 1, 0, 0, 0, 1, 0, 0, 0, 1 times RST. Okay, so if we go through this, right, if we go through our little thing, rigmarole, so left to right, top to bottom, then I've got 1 times R plus 0 times S plus 0 times T. Okay, next, if I go across left to right, top to bottom, I have 0 times R plus 1 times s plus 0 times t. And then lastly, if I go left to right, top to bottom, dot product here, 0 times r plus 0 times s plus 1 times t. And really all I've done is I've created r, s, t again, which is exactly the same. So this matrix didn't do anything to my vector. Interesting. And let's look at it again. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you've been doing a ton of row reduction, this sure looks kind of nice, right? This looks like what you would want your coefficient matrix to look like if you had a solution in an augmented system. So what we're going to call this is the identity matrix. And since it has specific dimensions 3 by 3, we subscript the I with a 3. But that's generalizable, obviously, to different things. And what made this identity was that it was the matrix that returned the vector to itself. It returned RST to RST. It didn't change anything, okay? In general, I sub n is the identity matrix of an n by n. So this right here, 1, 0, 0, 1, what is the size of that? That's a 2 by 2 matrix. So that means this is the identity matrix sub 2, I2. If I had 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, I'd say, okay, this is a 5 by 5 matrix. So this is the identity matrix I5, etc., etc. Okay, so there's that language, identity matrices. And then lastly, just a little algebra rule so that you know what you're allowed to do with this. If A is an m by n matrix, and we have two vectors, uv and rn, and lastly we have some scalar quantity, then we get these algebraic properties, right? So the first is that there's distribution. So if I am doing a matrix equation, I'm trying to compute a matrix times a sum of vectors, I can distribute that through. I can just do each of those individually if need be. And then there is some level of the constant multiple. So if I want to have a scaled vector, so say a vector u has been scaled by something, and I want to compute the matrix times that, sometimes it's easier to, especially if that constant's like really horrible, but it's nice to take out like a fraction that's ugly, you can take that constant all the way out first, and then just do the matrix times the easier version of the vector, and then after all that scale it. So you are allowed to do those things to make your life easier when you do computation. Okay, so that is all of 1.4. So on Wednesday we will resume and get on with it 1.5.